Simultaneous reaction. In developing the equilibrium equation and equilibrium constant expressions of section 16.4, it was assumed that there was only a single chemical reaction equation relating to the substance present in the system. To demonstrate the more general situation in which there is more than one chemical reaction, we will now analyze a case involving two simultaneous reactions by a procedure analogous to that following the previous chapter. These results are then readily extended to systems involving several simultaneous reactions. Consider a mixture of substances A, B, C, D, L, M, A, B, C, D, L, M, and N, as indicated in this picture. These substances are assumed to exist at the condition of chemical equilibrium at temperature T and pressure P, are in equilibrium at T and P. Chemical equilibrium. And are the two reactions assumed to be reaction 1, VA1 A plus VBB VC VA2 A plus VL L VM N plus VN N. We have considered the situation where one of the components, for example A, is involved in each of reaction in order to demonstrate the effect of this condition on the resulting equation. As in the previous section, the change in amount of the components are related to the values stoichiometric coefficients, which are not the same as the number of moles of each substance presented in the vessel. We also realize that the coefficients VA1 and VA2 are not necessarily the same. Disease substance A does not in general take part in each of the reactions to the same extent. Development of the requirement for equilibrium is completely analogous to that of the section 64. We consider that each reaction proceeds an infinitesimal amount towards the right side. This results in a decrease in the number of moles of A, B, and L, and increase the number of moles C, D, M, and L, letting degrees of reaction be epsilon 1 and epsilon 2 for reaction 1 and 2. Degree of reaction epsilon 1, epsilon 2. Now we can write the change in volumetry for reaction 1, DNA, stoichiometric A1, d epsilon 1, stoichiometric A2, d epsilon 2, DNB DNB d epsilon 1, DNL VL d epsilon 2, DN for the product NC d epsilon 1. Dn another product epsilon 1, another product also dnm and dn and d epsilon 2. The change in Gibbs function for the mixture in the vessel at constant temperature is dg T and P GA DNA GB DNB GC DNC GD DND GL DNL GMD NM and GND NN. Substituting the expression and collecting terms, we can write the change in Gibbs function at T and P, the d epsilon 1 d epsilon 2. It is convenient to again express each of partial molar Gibbs function in terms of G substituting to the previous relations, we can express that d, g, t and p d epsilon 1 plus delta G20 for each reaction feature. In this equation, the standard state change in Gibbs function for each reaction can be defined as for each reaction These equations express the change in Gibbs function of the system at constant temperature and pressure for infinitesimal degree of reaction of both reaction 1 and 2. The requirement for equilibrium is that the Therefore, since reaction 1 and 2 are independent, d epsilon 1 and d epsilon 2 can be independently varied. It follows that at equilibrium, each of the brackets in the previous relation must be 0, defining equilibrium constant for the two reactions. We can have ln K1 L. The expression for the equilibrium composition of mixture must be solved simultaneously. The procedure following in this section can be really extended to equilibrium system having more than two independent reactions. In each case, the number of simultaneous equilibrium equations is equal to the number of independent reactions. The expression and the solution of resulting large set of nonlinear equations require a formal mathematical iterative technique and are carried out on a computer. A different approach is typically followed in situations including a large number of chemical species. This involves the direct minimization of system gives function g with respect to variation in all of the species assumed to be present at the equilibrium state. In general, the dg for the multi-component system dg dmi, in which the gi are each given by the specific equation are in mole, n are in mole. However, the number of change in mole are not all independent as they are subject to constraint on the total number of atoms of each element present. This process then results in a set of nonlinear equations equal to sum of the number of elements and the number of species. Again, this set of equations require a formal interactive solution procedure, but this technique is more straightforward and simpler than that, utilizing the equilibrium constant and equations in situations involving a large number of chemical species. Coal gasification is the next section.